right. Hello. Welcome to a new year. This is the first open office of the year. I'm excited for it. I am streaming to LinkedIn, YouTube, and Twitter. That's right. This year I am not streaming to Facebook, or at least not for now. We'll see if I go back. I use a platform called StreamYard, which the plan that I have lets me stream to three destinations. And I thought I'd play around streaming on Twitter. We'll see how it goes. This is an open office I'm very, very excited for. I really enjoyed the last one I did. I've kind of been off for a couple of weeks, enjoying the holiday season. But the last live stream, the last open office that I did was live coding, which was a lot of fun, actually. I was a little nervous doing it because, at least at the start, because I don't know, it just feels very uncomfortable to code in front of people. At least I thought it would be, but it was quite enjoyable. So I might be doing more of those, seeing how I did enjoy it, and it seemed to get a good response as well. Which reminds me, if you have any questions during this open office, feel free to shoot a comment on the platform that you're seeing this on. Other than YouTube, I can't directly comment back, but that's fine because I'm on video and I'll respond live on video. And your comments and questions or whatever doesn't even have to be related to what I'm showing on the screen. Maybe choose your timing well. But I love to talk about all kinds of stuff, easily distracted in the sense of I love tangents. So Deos, contemporary ballet, let's chat about ballet stuff, which we will today, surprisingly enough with code. We'll be talking about ballet. Machine learning, which we won't be coding much, actually at all on machine learning. And then business model innovation is my other main topic, which probably won't show up today either. But without much further ado, let's hop into the application that we're going to be chatting about today. And that's going to take a quick moment because I forgot to share the screen that I need to in order for everybody else to see what's going on. So here we go. Let's use this layout. The IRS. I have an application where I'm working with nonprofits. So we're very interested in nonprofit information. And there's plenty of resources online to be able to do searches. ProPublica, there's open990.org, which I'm actually going to pull that up because it is a fantastic resource if you haven't used it and you're interested in nonprofit organizations. You can basically type in the name of the organization you're interested in here. Let's see here. I'm going to pull up American Ballet Theater or New York City Ballet. We'll do that one. So here's just a quick preview. There's all kinds of information in here, such as like when they were formed, their organization type. You can take a look through and see who their director, president, CFO. You can look through their different programs that they host and how those dollar amounts have changed in their expenses, revenues, and all that type of stuff. How many people they have voting, how many people they have working for them, whether they lobby or not. Just all kinds of information. Being a nonprofit, it's required to report this type of stuff on the 990. So we are interested in using that information for all kinds of different things. But first we have to get access to it. And using a web browser like I just was can work if you're investigating a couple of organizations. But if you want to do some market analysis, right? Like I want to take a look at all of the ballet companies in the United States. What sort of insights can I get if I did a market analysis on all of those 990 returns? that would take me forever to dig through all of that data, especially through a platform like that. And I might even have to pay to be able to access all those records. However, the IRS does make this data available, and I'll show you how to get there. If you go to irs.gov, go up to File, you can click on Charities and Nonprofits and go to Search for Charities. And there's a couple of different paths you can go from here. They have this exempt organizations business master file extract, which you can go and take a look at the list of exempt organizations by, a CSV file for each state. That kind of tells you whether they currently have status or lost their status, it was revoked or something. So that's kind of a high level look at it. But what we're taking a look at today is the tax exempt organization search bulk data downloads. Very long title names. So what's particularly interesting in here is you can read through all that stuff, but we're going to look at this Form 990 series, and we can go back to 2015 and get a handy dandy XML format, which is going to make our analysis much simpler than trying to work with PDF files, which they also have down at the bottom here. So all this information is free to access. I ran into a problem though, and this is the meat of what we're going to talk about here. If you go to download this data, it's not like this nice web interface that we were just looking at earlier with 990, open990.org. For all of the organizations submitting information for 2021, they split it up into 4 different files. And if you were to download this file, which I'm going to cancel, it's hundreds of megabytes, which hundreds of megabytes by today's standards is not a massive file. But if you're going to be working with serverless functions, working with tens of megabytes is fine. Working with hundreds of megabytes can either get expensive, whether you have to have a ton of memory available on the function, the instance, or it could just take a while to process. So we're really interested in, especially if I'm looking at ballet companies, that's only a very small subset of these hundreds of megabytes here. So is there a better way to extract out the little bits of information that I need from each of these 4 files? Well, the answer is yes. But it took me a little bit to figure this out. So the key for me on this is that these are all zip files. And I did not know much about the actual structure of a zip file other than it's a compressed group of files, right? Like it's intended to save bandwidth, save storage space. But of course, on Wikipedia, you can learn a whole bunch more. And what I found that's really interesting is taking a look at the structure of a zip file. They have this really handy visual here. If this whole thing, I'm going to make this larger so it's easier to see. If this whole thing is your zip file, each of these light blue sections here are the actual data of each file contained within this archive with a little bit of header information. This header information is all collected and slightly expanded on when it's stored in the central directory, which just so happens to always be at the end of the zip file data. And to make things even easier for us, at the very end of the central directory, they have a very special record called the end of central directory record. So why am I talking about this? Well, the very interesting thing is if we could get that end of central, let me see here, end of central directory record, if we could get just that information from the zip file, we would know how, well, let's see here. We would know the offset and the size of that entire central directory. So then if we're able to grab the central directory, we would have the complete list of files and their relative sizes within the entire zip archive without having to read the entire file. So in theory, this is great, right? If I have a zip file on my computer, say I downloaded this and I'm coding in Python, I could open up that file in binary mode, seek all the way to the end, and read that end of central directory record and take a look at the whole central directory, and voila, there we go. I can see all the files in there. I didn't have to read through the entire file. The problem is this file isn't on my computer, so it's on a server somewhere else. And so it got me wondering, can I just read parts of files instead of having to read in the entire zip file? And if you haven't learned by now in this live stream, when I ask questions like that, the answer is always yes, you can, which blew my mind. I thought, I mean, it makes sense that HTTP enables this sort of activity, all standard, or not all standard, but a large amount of servers out there support this. There's a specific header you can pass in an HTTP request that's called range, which allows you to specify the specific bytes of a file that you want the server to return. So when you include the range header and specify the specific bytes, you say, hey, IRS, I want this first file here, this first zip file, but don't give me the whole thing. Just give me the last 2 kilobytes or the last 500 bytes or whatever size you want or need in order to read, this end of central directory record. And the reason why we only grab that is we don't know how big this central directory is. So what we're going to do here, and I'm going to stop burying the lead, we're going to make a request that's going to get this last record, this end of central directory record, inspect that data structure, which we can see how it's structured here. We're going to inspect that data structure to find the offset and the total size, and of course, the number of records in there. And what that will do will allow us to make a second request, HTTP request to the IRS's servers, to get this entire central directory, or chunks of the central directory, depending on how we want to balance number of requests with size of requests. Once we have this central directory information, I can inspect the files that are contained within there. And instead of having to download all of this data, I could pick the 1, 2, maybe 5 files out of this entire zip file that I care about. And just to, demonstrate why this is helpful is here's an example. Ooh, I got to make this larger. On the right here is an example of an XML file that's contained within one of these zip files. And what you'll note, if you take a look at it, is it's only 503 lines, which if I can quick figure out View and Explorer. Yeah, each of these return files are less than 100 kilobytes. Right? So if I'm only interested in 10 or 100 of these files, I only need at most a couple of megabytes from the hundreds of megabytes in this zip file. So not only am I going to be saving a lot of bandwidth by making a couple of additional smaller requests than just one large request, which I'm sure not only my own personal bandwidth, but the IRS, I'm sure, would appreciate that we're trying to minimize how much bandwidth we're using from them. It also is just making it so I don't have to store a whole bunch of information that I have to then later delete or manage or, don't care about. So that is the basic structure of what I figured out. Is rather than download an entire file within a serverless architecture, so I usually use Azure Functions, there's a limitation to how much memory it gives each instance of the serverless function too. We're going to make, to get a single file, we're going to make a total of 3 requests. Get the end of central directory record, get the central directory, and then we're going to inspect that to request the one file that we care about. And that's it. So let's take a look at code. I'm going to pause here and grab a quick drink. So what I wanted to do with this is, while I'm very interested in ballet companies right now, I think this could be a really handy Python library for a lot of different use cases. And some of the other tools out there have tried to do this balance between exposing the raw data and then putting a good but like industry specific overlay on the data, right? Like process it in a certain way. And I think there's an opportunity for a middle ground here where it's more of like a developer tool, right? Like, let's make this easy to create a new data set, right? Because if I were to do work I do work for Dance Data Project, who cares immensely about ballet companies, but doesn't care at all about other nonprofits such as, I don't know, animal shelters or things of that nature. This tool would enable me to very quickly download the relevant data for that particular application and structure it in a way that then could be used to query and find all the other interesting things. Like, maybe we care about the total expenses each year from these organizations. So looking over here, you could look at how much cash they started and ended with at the end of the year. We could do that for every company of interest. So the tool that I'm interested in making isn't to provide answers and analysis directly for all nonprofits. This tool is looking at at creating that data set that you can do whatever analysis you want on it without having to just download all of the zip files, extract out all the XML files, figure out how to handle all of the different versions of the structure of the XML, but to just specify with basic data structures what information you're interested in and extract that out into a usable data set for yourself. So that's what we're aiming to build. And over the winter break, instead of prepping open offices and things of that nature, I just got to coding and making this happen. So let's see here. We're about 18 minutes in, 20 minutes in. I think we've got some time to go through this. So I'm going to just start walking through a little bit of code and how I chose to solve this problem. There is no guarantee that this is the best way to solve the problem. But I think it might be interesting to just walk through a little bit of how I've structured this Python code and at least my initial attempt at solving it. So I have a total of two Python packages here, one called IRS, one called zip. We'll focus in on the zip one first. This is all the utilities that I made in order to interact with the zip files. Now, there is already a zip file Python package that if you have the data locally, it's super easy to use. It'll already do all of this inspection of the central directory. I think it's actually called just zip file. If you do a Google, zip file. If you do a quick Google search for it and all your data is local on your machine, you don't have to interact with an HTTP server. Just use this, right? Like, there's no need to use my library because this will already parse all that info. The aim of my tool that we're walking through right now is to be able to save bandwidth and make this able make the capability available to serverless functions, which have to be careful with how much memory they use and process things quickly. So somewhat of a special use case. So what I have in this zip file here is a couple of different things. First of all, I have a couple of different models here, and we'll take a look at this eocd.py file, which is the end of central directory record. So if we go back to the Wikipedia documentation on the zip file format, that's this last little dark purple stripe here. That is the end of central directory data record. And we can inspect what those bytes and bits do in this table here. So all I did was I took the information within this table and I made a class to represent that, that record as an object. And I really like the data classes package, where you basically wrap your classes that are intended to be used as data structures in a data class, because that can make a lot of things easy. So for example, I don't have an init method defined on this class, because data classes makes it for me dynamically based on what sort of fields I make available here too. You'll also see I like to type things as much as I can. Python is duck typed, so it is strongly typed under the hood, but you often don't have to specify types. I do this because it can be very helpful after you haven't touched code in a while to know specifically what types something takes and returns. Python can often figure it out for you, but I just find it really helpful for documentation purposes to just spend a little extra effort and document the types. You'll also notice here frozen equals true. So what data class allows you to do is, it's not, there are workarounds, but in short, when you say frozen equals true, that means when I construct an object of this class, don't allow it to change. So this is kind of like making a static data structure, right? Well, not a static data structure, but one that once you set the data, you can't change it. We got a quick comment from Rahul Gupta. Yeah, thanks for joining. Yes, definitely a recording of this will all be available. So glad you've enjoyed the content up to this point. Yes, so frozen data structures, very helpful, because sometimes later in code you forget that, if you change some of these properties on this object, it can wreck things downstream. So we're just preventing that from happening once we construct it appropriately. And then I make a couple of class methods. I guess just one class method. So the reason why I do this, and I'm just going to type it here, instead of in some other file doing eocd and then having to type in, disk index equals 0, cd start disk equals 0, right? And go through that entire automatically generated init function, I'm going to instead expose the method from bytes right here, where all I need to do is pass in a byte array, and it will go through and construct this class for me. So the reason why I like this is I think it makes a much nicer developer experience for working with this sort of low-level data structure, where all I need to worry about is make sure that the data that I pass this function has the information it needs to construct this for me. So once I make this class, you don't need to know all the details of how an end of central directory is structured. You'll just be able to access all of these parameters after you pass in just a list of bytes. And what I also do here is I've got a very quick and dirty scan through all the bytes, because if you notice, there's a signature. So if we go back to the zip file format, at the very beginning of this end of central directory data structure, they have a signature that you can look for in order to identify this information within a byte stream. So whatever bytes I pass in, I'm going to scan from the end to the beginning looking for these magic 4 bytes. And if I find those magic 4 bytes somewhere, I know all the following bytes, what they represent according to this data structure here. The next 2 bytes is the number of the disk. The following 2 are where the central directory starts, all of that good stuff. Once I find these 4 bytes, I'm able to parse out all the rest of the information. And then you can see here with this CLS, which is passing in this class EOCD here, I call the default constructor with all of the relevant bytes set to create all of these fields, and then I return it. So let's take a look at what that looks like in code. If I think it's probably best seen in IRS here. Maybe? No. It's been a few days since I've looked at the code. You know what? Here's a good way. Look for where I use it. Boom. So here's an example of that being used. So I use the requests library that Python provides. Well, you have to pip install it. It's not a standard library. So install the package requests, and then I can use that request package to submit a GET request to a URL. And here you can see I'm passing in a certain byte range, which I'm passing in -65556. This is the maximum size of a end of central directory record. It has a variable size because in the standard, as we can see in the data structure, it does allow for comments or a comment. And one of the fields specifies with 2 bytes how long that comment could possibly be in bytes. So I took the maximum, 2 to the 16th power, 2 bytes, that many bits, I should say. Figured out how many bytes that was and set this to the maximum. So I figured out how long could a standard end of central directory record be. And this syntax here tells the server that we're making the request to, hey, look at the last that many bytes, right? Because this is how many we could possibly need to look at. And then I pass that response, those bytes, right into this end of central directory class, the method from bytes, and it constructs that object for me. So I don't, after I've designed this object once, I no longer need to worry about the implementation details. I now have this fully exposed just by passing the bytes given to me by the request, which I think is an excellent developer experience. So now what I could do is just do .cd offset, and now I have access to the offset within the zip file of where the central directory starts, which is quite handy, and I don't need to know how long that is or any other information. It's just exposed for me to use. So that is this. I did make a function here that I'm not using right now where I can write out this object. So if I constructed an end of central directory object, I could write out the specific bytes to a byte stream in order to create my own zip file, but I'm not actually using that right now. This is part of my development practice. When I was designing this class, I needed this at one point. So that is that data structure. So this is all under a folder called models. There's a couple of other models in here. We have a very similar structure for the central directory file header meta, which if we go back to our reference here, that's all of these files in the central directory indicating, hey, this is a file in the zip file. This is another file in the zip file. Here are all those pieces of information. And what that header gives us is actually a lot of information. Of course, it starts off with a header signature so we can find data in a byte stream of it. And it gives us the minimum we need to read it in terms of version, the version that was made by, all kinds of other things. It's got a CRC check to make sure that you read the data correctly. Tells you the compressed size, which is very important, so we know how much data to read when we finally extract out a file. It tells us how long the file name is, which we then can use to actually read what the file name is, what disk it's on, all the information that you would need to know about a file in order to read that file out of the zip file, the zip archive. So that data structure is here. I won't go into any more detail about all these fields. You can look that up in the documentation. But you'll see I've got the same thing, a from bytes method here, which handles all of those implementation details for you. So all you have to do is pass in bytes rather than figure it all out yourself. And I have the 2 bytes method to be able to write out these headers. But I also have a gen from bytes function here. And why this is important is what is happening here is at some point I want to not just get one. Whoa, what's happening? I don't want to just get one file header meta. I want to be able to get the entire list, to get that whole central directory. So perhaps it's not the best implementation to put it within this class. Actually, I might, yes, that is what this is for. Yeah, so what this is going to allow me to do is I can pass in a much larger chunk of bytes, and it will iterate through that large array of bytes and yield out, so return out a list of records of these central directory file header records. So that's doing it in a generator style, which is why I prefix it with gen, just as a hint to myself, but you can tell that it's a generator by this yield. And you can see normally I would include the type, which I guess I got lazy here. So that would also indicate to you, oh, maybe that's why I didn't do it, because I couldn't reference the same class within the class. Anyway, so what this function's intended to do is after we've received and parsed out this end of central directory file record, we know where the central directory starts and how long it is. And so I can do another request that gets those specific bytes from the server. And then I pass all of those bytes, or maybe some subset of them, into this function. And rather than just create a single CD file, central directory file header, it's going to start iterating out all of the central directory file headers it finds within those bytes. And again, I use the generator approach because I'm trying to keep memory use, like in-process memory use, low by only asking for data when it's actually needed, as opposed to compiling that entire list and then returning the entire list as a return. Yeah, so that's how I actually end up getting all of my CD file headers here, and we'll see where that's used. Yep, so that's within the zip file here. Perfect. So you can see after we get some large section of bytes, we pass that data directly into this function, and we're going to iterate through all of these specific central directory file headers. So that's how we get all of these individual file headers. And then once we have that, we're able to then go and find where each of these files are specifically within the zip structure. And that is this last model in here, file header. which I'm going to just very briefly skim through this because it's all very similar structure to before. We've got a frozen data class. We've got all these parameters that we want to extract out from the raw bytes. We have a from bytes method like we do for everything else. And we've got this 2 bytes in case we want to write back to it. And then I have a very special function here called from central directory. Why this is interesting, or why I created this function, is because if you take a close look at this local file header, which is the dark blue stuff that happens right before the actual file data, if you look at all these fields, it's the same information as what's in the central directory file header, except the central directory file header has a couple of extra things, like it has file comments, whereas the local file header does not. And the position of the bytes that are of interest are slightly different. And of course, it doesn't have the relative offset from the beginning of the file to it. So to say it more succinctly, this header is a subset of this header. So if we already have this header because we read in the central directory, we can create this, this local header from that central directory. Again, this is only really important when we want to write out to bytes, because otherwise we do want to make sure we find that local header and read it and make sure that it's the type of information we expect. Otherwise, someone could send us malicious content. But that's a quick way when we're writing out data to take a central directory and get a local file header as we're writing out a byte stream. So that is the end of the zip models. If I were to go in here and take a look at how I collect all of this together, to use these models at the level that I described would be a little bit arduous, even though I've tried to make the developer experience pretty good. So what I really wanted to have was a zip file object where there's a sort of HTTP flavor of it, which is what we're trying to accomplish here, where you can specify just a URL and it will go and get all of this metadata for you and handle all of these requests in the background. So you don't even have to think about end of central directory records and all of that stuff. So what this class is doing here, and note it's not frozen, you can, when you create, actually let's see where this is used. Right. So when I made this, we'll start here. Maybe I should have started from a high level to begin with anyway. Who knows? What I wanted to do from a high level is say, hey, I want to get the metadata from a list of URLs. So for every URL in that list, I want you to get the metadata from this HTTP requests from this URL. And once I have that metadata, the representation of that file, without fully downloading the entire file, I want the code to then go through the list of all of the files in that metadata and do something with it. Right here, I'm just going through and looking for certain fields within each file. And that's the particular use case that I'd be using this library for. But the key here is this library would give you access to the metadata of a zip file, handling all these background requests for you to get the end of central directory record, to parse that central directory and figure out all the files that are in there without downloading the whole thing, and then expose all of those files through an iterable. So you can just do .list. So this is where I've implemented that. When you open the file, when you call this from HTTP, as we saw up here how I construct one of these objects with a class method. What it will do is it will go and get that end of central directory file, form it into an object, and then return a zip file object which keeps track of the URL for later HTTP requests, as well as a copy of the end of central directory record. Then once we want to go through and call list and actually start iterating through all the files within the zip file, we have this list function defined where it already knows the URL, it already knows the end of central directory record. And so what it's going to do is it's going to intentionally chunk up requests. So if the zip file is small enough, it can grab all of the metadata on that central directory in one go. Right now, I think I have it specified to 1 megabyte at a time, but you could specify that in the call to list. Otherwise, it's going to iterate through chunks and go through and inspect this end of central directory file, and it will then go and get these central directory file headers, and for every single one of those headers, it's going to yield out that header metadata. And once we have that header metadata here, we can then go and open up that specific file, which that open function here says, okay, when I call open on this function, passing in some central directory file header data, I know all of the information to know where in the bytes of that zip file I need to request to just get specifically this one file. And in this case, I'm going to assume there's other compression methods a zip file can have, but for now I'm only using the IRS data, and they use the same compression. I specify it to be the deflate algorithm here with these bits. And so it will get that compressed data from the zip file and decompress it on the fly and return it. So in my stream function here, just to recap before I go into a couple of other things, we open up a URL that we're interested in. In this case, we'll take a look at this one, and that gets the end of central directory record, which is this last little purple line here, which describes the rest of the central directory. Once I have this reference, I can then iterate through all of the records in the central directory right here and use those central directory headers, the metadata, to then call an open function, which will then go out and request a very specific file based on the metadata we passed it. And after it's downloaded just that file from the server, not the entire archive, it'll decompress it and pass it back as data. And then we can do what we want with that data. So that is the whole zip file, downloading the data, exposing out the internal workings of a zip file, and allowing us to reduce bandwidth by only downloading the parts of a zip file on a server that we're interested in. And after all of those implementation details, which I'm sure I will improve over time, we get this really, really nice interface of specify a URL, go through all the files, grab the files we're interested in. So what you see here in the middle is me going through that metadata and finding out what files are of interest that I want to open. And so I think now I'm going to go into the more IRS specific code that we're interested in here, because what the IRS gives is a zip file that has a whole bunch of the XML files that we're interested in. So XML also has a syntax, a standard associated with it that we can learn to parse. And like all things in serverless functions, I like to do things as streams as opposed to batched processing. So what I would like to have is, instead of having to just read in the entire file and then process the entire file and then close the file, I want to set up a byte stream. The server's not going to give me byte by byte. That would be really inefficient. But I don't need to load the whole file into application code memory. I can let it be in the system call area, the system memory, when it downloads it from the server. So all that to say, I like using stream processors for XML, and Python has a very handy library, XML, where they expose a special reader, Sax, S-A-X, which I don't know exactly what that stands for. And since we have the web available to us, we're going to just quick Google it. Sax stands for Simple API for XML. So it's an event-driven approach. And so what that means is, let's take a look at the IRS code here. This library, the Sax, the XML Sax library, what it wants is for you to pass in data and a handler for that data. So what this library will do is it will open up a file or reference a byte stream that you give it, and it will pass events that occur as it's reading that file to a handler. So what we need to do is we need to specify a handler that appropriately handles the events as the file's being read that we care about. And so that implementation specifically for a file from the IRS, I've defined like this. So there's a number of different events, and there's only a few of them that I actually care about. So we're extending the XML Sax packages class called content handler, which allows us to override a couple of elements, called a couple of functions. The ones we're interested in are start element, end element, and characters. So let me make this concrete here. Oh, shoot. If this were to be processing this file over here on the right, it would load up this information, and the very first thing it would do is it would emit an event called a start element event that says, hey, there is a new element that started, because we've opened this up, this structure, and it's called return. And then the very next event that it would emit would be the characters associated with this element, which you can see there is no content. It's just a structural element. So then the next event would be another start element event where it specifies the name is return header and passes in these attributes as well. That's associated with the start element. And once again, there is no text associated with that opening because it's a structural element. And then finally, we get to some interesting stuff. The next event would be a start element saying, hey, this is a return TS, return timestamp. So this is the time at which the return was filed. That would get emitted here to the start element. And then it would emit a characters event, which would pass all of this data to this function. And then finally, it would call the end element function as an event. So this is the sequence that we care about. We care about, if we were trying to read this return timestamp, we care about seeing that a start element event occurred that contained the name return TS, and then we want to capture the content, the characters that occur after that event, and then we want to stop listening to the characters that get passed to us once that element, return TS, is passed. So this is why XML is much nicer to process as a stream than JSON, because it keeps track of when certain structures close in a way that is easy for computers to deal with. In JSON, this would be like an open curly brace with a key, a value pair, and a closed curly brace, and it'd be really hard to tell without a lot of additional tracking of curly braces what you're opening and what you're closing. Whereas in XML, it's a lot more, it's a lot easier to work with. So love XML for that reason. So what you'll see here is I have this special class that, yes, does handle these three types of events. But what I've chosen as an implementation detail, at least for now, is to handle the stateful nature of that stream of events. I want to create finite state machines, which is a really handy tool from computer science to represent, it's used for a lot of different things, but it's a really great one for handling the context of a byte stream, right? Where you need to keep track of information over time, but you don't want to have to keep the entire file in memory. So what I have here is a function that allows me to register a new finite state machine with this handler here. And if you're interested, I don't think we're going to get to it today. I do have just a quick finite state machine code for the object up here that's handling some of these things that essentially, well, I guess we'll get a little bit into it as we look through these elements here. So in my IRS code, in the application code, what you need to do is you need to create this handler that you pass in to XML Sax. And we're going to specify a list of finite state machines. So there's a couple of different state machines. There's a couple of pieces of information that I want to extract from each of these XML documents. In this case, it's the EIN, the employer identification number. I want to get the company name, and I want to get the tax year of the return. So we can find that information here in the XML file under return, return header, filer, EIN, there's the number. So how I've structured this finite state machine to work is to say, hey, here's the name of the state machine, the finite state machine, and the path that I want it to extract text from is return, return header, filer, EIN. So how my state machine works is for every event that's emitted, every start element event, it's checking this list and keeping track of where it is in this list. And once this specific sequence of start elements, return, return header, filer, EIN, is observed, it starts memorizing all the text that comes after that until this last one, EIN, that element is closed. If it observes a pattern other than this, then it ignores all content. So at the end of scanning through this file, I will have 3 state machines, each containing one piece of information that I can reference as a key value pair, where at the end I can say, all right, give me the EIN value, give me the company name, give me the tax year. And that happens when I parse with this handler. And then you can see this is where I extract out that data and make it usable. So that's what's happening here. Within the handler, all it's doing is every time there's a start element event, oh, this was a debugging thing. That doesn't matter. What it does is it iterates through each of the finite state machines and passes that start element event to the finite state machine, the update. So it's saying, hey, finite state machine, there's an event transition. Here is that transition. Handle it as you will. Every time there's an end element, we don't care because we don't really need the finite state machine to track that info. And then characters, it also will iterate through each of the finite state machines, but rather than just pass the characters directly to it, the finite state machines only will track content that it cares about, right? That we specified here in this list of start elements that we care about. And so for each of those finite state machines, this handler says, hey, let's then inspect the finite state machine and see if we're in a state in which I guess these are poorly named variables. We're going to see if we're in a state which indicates that we need to write content, right? So there's three states. We're either seeking, we're listening to these start element events, waiting for content. And once we find the right position, we enter this write mode. And once we're done writing, we reach the end of that element, we go into a complete mode, which prevents us from doing anything else with the state machine. So when we receive content, we're going to inspect each of these finite state machines and say, hey, are you in the right state? Because if you're in the right state and we don't have any content yet, I want you to save all this content off. Otherwise, who cares? We're not in a right state. You don't need to save this content, and we'll move on to the next iterator. Once all of the finite state machine states are not in a seek mode, they're either writing or they're complete, we're going to stop iterating. So this little section of code, all that's doing is if all we were extracting out was, actually I can show it right here. All we're extracting out is this EIN, the business name, and then the tax year, which is at the bottom here, or at this section here. Once we reach this point in the file, all of our finite state machines have gotten the information they want, and we stop iterating, and we don't even read the rest of this file. So that's the advantage of stream processing. Once we know we have all the information we need, we can just drop the file handle, right? Like we can close the file stream and we don't have to read any more information or waste any other time processing data. So that's what I love about stream processing. So that's how this is structured. Once we have metadata and we get the data from the server, we can specify this handler that says these are the specific pieces of information that I care about and the structure that leads to that data. Run it on this file that I extracted from the HTTP server. And then as soon as that's done, I'm just going to look at the output of all those finite state machines and compile it in a dict comprehension, a dictionary comprehension. So now I've got a key value list of EIN as the key, and there's that company's EIN number, the company name as a key, and the value of that actual name, the tax year and the tax year. So I could add as many finite state machines as I want here, one for each piece of information that I care about extracting out of this XML file. And as you can see here, I have an iterable where I can then go and do that over every single file that's of interest. And the whole premise of this is that I am not downloading the entire zip archive. I'm only downloading the parts that I need to have and only processing the parts of the resulting file that I care about in there, only to the extent that I need to. So I can save on bandwidth, I can save on processing time, and I can keep this very, very low cost and fast for a serverless function where I like to use Azure functions to do this type of stuff. So the rest of this, ignore. It's me playing around with my little API that I made of access this URL, iterate through all the files in that URL, and then open up and do interesting things with them. But I hope that this was informative on the zip folder structure, on XML and how to process it, some Python code, some interesting headers that you can use with HTTP requests to reduce bandwidth. And of course, if you're interested in processing 990 data, you've got a couple of market analyses that you want to do, or you think there's some interesting use cases out of that, I'd love to hear some feedback because if this sort of package of code could be useful to other people for efficiently extracting information from 990s, yeah, I'd love to continue improving this not only for my own use, but for other people's as well. And of course, we can add in other processing. It doesn't have to be just one type of zip compression. I'll probably continue expanding this out as I find other data sources that are very, very large zip files and make this easy for us to extract small pieces of information from very large data sets. So there we are. We've reached the end of this open office. As I was going to say, as I warned, because I don't know how often people care about deep technical dives like this. But this one is a particularly deep technical dive. I breezed through code that I wrote very quickly for fun, so it's not perfectly well structured. Not all of my open offices are like this. In fact, this is the first one that's gone this deep. That's sort of the content I had planned for this. To make up for all of my missed open offices, it's not really making up for it, but I do have a live stream planned for tomorrow, which is Thursday, January 6th. I'm quite excited about this. It's very different content. Over the last year or so, I've been following a number of people on Twitter who've helped me understand marketing better. So since I help run a professional ballet company, we have to get the word out. I'm an engineer. I know how to do code and data and all this type of stuff. What I don't know how to do super well is market, and specifically paid advertisements on Facebook, which is a great place for ballet companies to be reaching out to potential audience people. So I have a guest tomorrow who's going to be joining me tomorrow, Thursday, January 6th. We're going to be live streaming at about 6 o'clock Eastern time. He's in the Pacific time zone, so that's 3 p.m. Pacific time. And his name is Charlie. He goes by Charlie the Disruptor or CT the Disruptor on Twitter. He has a wealth of knowledge about Facebook paid advertisements. I've been implementing the things that he puts out on Twitter about how the right way to do Facebook advertising. And I can tell you, I see the difference, right? Before I was trying to do very high levels of targeting, trying to get that audience size down as specific as I can. And I just saw all my costs going up and my results go down. I'll let him talk a lot more about his approach, but in short, targeting broad and having this experimental approach where you're allowing the algorithm to do its work is, to a machine learning engineer such as myself, not just intellectually stimulating and makes me happy that the algorithm does a better job than people sometimes. But not only does it make a lot of sense, but I've seen its impact, positive impact on my ad campaigns. So yeah, if you're interested at all in Facebook paid advertising, especially if you're a direct to consumer business, we're going to be chatting all about that stuff tomorrow. So make sure you tune in. But anyway, thanks for joining me today. Hopefully you got a lot of good value out of it. All right, take care.